session is Tony Acin, and she's going to be talking about local orthogonality, multipartite principle, and quantum correlation. Thank you, Tony.
Okay, so good afternoon, everybody. Yeah, so I'm going to tell you about something that we are doing now at ICFO, the institution where I work. So I'm in the CREA professor in Barcelona. CREA is a research institution in Catalonia that pays salary for people to work in Catalan institutions. So I'm paid by CREA to work at ICFO. So this is why I thank them whenever I give a talk, like today. And these are the people that work with me in this project. So all of them are based at ICFO. So we have people from my group, postdocs, PhDs. And so what we do is the following. We work in the what's worse scenario. So I assume that most of you are familiar with this, but still, for the sake of completeness, I will give an introduction to this scenario. So what we have is that we have distant parties that have access to a device. And in this device, they can put a classical input and they get a classical output. So the classical input is labeled here by X, X1 for the first party, Xi for the ith party, Xn for the nth party. And the box produces, after you put the classical input, it gives you a classical output, which is labeled by I. So here, if you think physically, this can be understood as you prepare a state of many particles. You send the particles to different parties. The parties can choose among m different measurements. This is why I chose the n possible values of your classical input going from 1 to n. So you choose between n different measurements. And then you, as a result of the measurement, the particle gives you a possible result among r possible values. Okay, this is why you have this here, the result, going from 1 to r. And you collect the data, and you keep doing the experiment, you collect the frequencies, and then you describe all what is happening in this very, say, macroscopic description by the probability of getting the outputs I given the inputs x. So this is the description. And the thing that you don't want to make any assumption about the process, that in principle you don't want to make any assumption about the internal process, the internal working of the device, how the device produces the output given the input. You want to make a very general assumption about these devices. And why this problem is interesting? I mean, in principle here you can imagine that you can put, what is this? This is just probabilities. So these are positive numbers, and you take the same combination of inputs and you sum over the output. The numbers have to sum up to 1. Because it's something very, very innocent. But the problem becomes interesting because we believe that these devices have to satisfy some physical principles. And then I think that physical principles translate into limits on correlations. So whenever I would say correlations, I would mean this vector of probabilities. So when I mean the vector of probabilities, I was saying, if you think of the simplest example, it's just an example where you have two parties, two measurements, two outcomes. And your vector, this vector of numbers, maybe to be consistent with my presentation, is A1, X1, X2, is just P of getting the result 1, 1 when you measure 1, 1, result 1, 2 when you measure 1, 1. Well, it's very simple, no? And you have another 4 component vector for the other combination of inputs, other order. So these are positive, and the sum is equal to 1. This is what I'm saying in the previous slide. Okay. Well, I mean the size of the vector will depend on m and r. So these are positive numbers, so they sum up to 1. But now let's put let's assume that they should be compatible with some physical principle. So something that I will assume during my talk is that there is no communication among the devices. When you put the input, you get the output. Okay, so the moment you put the input and the device generates the output, there is no possibility for the device to exchange any communication with the others. Okay, if you are completely paranoid, you can think that you make this process define space-like separated events. Otherwise, you can think that you have some shielding capabilities, and you can really shield the devices so that they don't communicate while they produce the output given the input. Well, this simply means that the correlations that you see should be such that they don't allow you to send any communication faster than light. Because in the worst case, I make things space-like separated, and then it cannot be that if someone makes a measurement, it can affect the statistics I see. Because if that was possible, he could send information to me. And this simply means that the correlation that you see have to satisfy this linear constraint. When you sum over the results of a subset of the parties, what the other party sees cannot depend on the inputs of the other parties. Otherwise, you could use this for things like that. Well, you see that here you have a non-trivial constraint given by this number that I have to satisfy. Okay, this is why things become interesting, only because you assume that you cannot violate Einstein causality with these numbers. Okay. Sorry. So then you can say, oh well, I mean this is seemingly very interesting, but now I want to classify those correlations I can achieve by classical means. So this is the following. You can think of the devices that have been prepared by me. I prepared the devices for you. I'm the provider. So what I did, I wrote some classical instructions on the devices, and I put these instructions on the devices, and I'm giving the devices to all of you. Okay? And this, I wrote the instructions taking a classical pen and writing on a classical piece of paper. Okay? And these instructions simply say on the device, okay, if the user input a x something, you produce the output a equal to something. Okay? This is classical instructions, classical program, classical computer. And then you can see that the correlations that you can get are given by this form, which is the standard EPR or local hidden variable argument. But it has an operational meaning. It simply means that you prepare the devices, you wrote a classical program, and you gave this device to someone else. So what you can see is that the correlations that you see can be written as the sum over the instructions in this. The instructions that I mentioned before in this mathematical formula are given by the lambda. And you see that the output of each of the devices depends on the input and the instructions that were inside the device. This makes a lot of sense. And as we know, not all probability distributions can be written in this form. And the set of classical correlation defines a convex set, and you can see that it's a polyton. And of course, in between, what we are mostly interested in is quantum correlations. And in that particular case, we also know what this means. It simply means that the probability that you see should be written as a trace of a quantum state with some measurements for each of the parties. So again, I assume there is no communication. This is why you see there is this tensor product in between all the measurements. Okay, so I have the trace of a quantum state which defines the state that was prepared by me. Now I'm not preparing classical instructions, but I'm preparing quantum instructions. So I come, make some correlated quantum particles, I put these correlated quantum particles on the devices, and I give the devices to you. And you start making these measurements and getting outputs. And this is what you will get for sure can be written like this, otherwise not quantum. Okay, so what we know is that the set of classical correlation is strictly smaller than quantum correlations, and this is because classical correlations, as I defined, correspond to local hidden variables models. Local hidden variable models satisfy Bell inequalities, and quantum correlations violate Bell inequality. So we know that quantum correlations is strictly larger than the set of classical correlations. But we also know, and this was, well, it wasn't a paper by Silverson, but I think it was emphasized by Popescu and Rowley, that non-signaling correlations is strictly larger than quantum correlations. Okay? So in principle, I can give you some vectors of numbers that they look innocent to you because they don't allow you to make any faster than light communication, but they are not that innocent because if you had these correlations in nature, it would mean that quantum mechanics is wrong. Okay? Because there's no way of getting these correlations. Again, if you want some sort of pictorial way, I'm very bad drawing, even with a computer. But okay, there would be the set of classical correlations, which is here, the set of non-signaling correlations. All of them are convex sets. And in between, there is a curved region which corresponds to quantum correlations. And in the last years, there is a sort of effort trying to understand why we have this boundary here. Or if you want, why we don't have this point here. It doesn't contradict any, say, physical principle. Well, it contradicts the fact that there is no Hilbert space and operators and blah blah giving you these numbers, but why? I mean, perhaps some people argue, and I think it's a valid argument, that it's not a very satisfactory principle, the fact that you don't have a Hilbert space where you can find an explanation for these numbers. So people are trying to see why you can exclude, how we can exclude these supraquantum correlations and really get the quantum boundary simply using some well-motivated principles. And actually people think about the use of information principles to answer this question. And to my knowledge, one of the first results in this direction, which I find very nice, is by Wim van Dam in his thesis. And what he showed is that if you had access, if you had access in nature to this point, that is called the nonlocal machine or Popescu-Rowley box. So imagine you had a way of making this correlation between two separate parties. Then these two separate parties could solve any communication complexity problem at no cost. Okay? Communication complexity, it means that, for instance, I want to to meet with Down. I mean, we have to fix we want to meet in next month, and he's here in the UK. I'm back in Barcelona. So what we have to do, we have to compare our agendas and see when we can meet. And of course, you can understand that I will say, okay, can you come on Monday, blah blah, and you say, no, I have something. Can it be on Tuesday, blah blah, and we have to exchange some communication. Okay, this is a communication complexity problem. Well, this problem become trivial if you had access to these boxes. And trivial, by this I mean that the amount of communication that we have to exchange does not depend on the size of our agenda. And in principle, you believe that this cannot be possible. I mean, if you have very busy agendas and very big, I mean, we will need to exchange more bits of communication. So, I think this principle, let's say, communication complexity is non-trivial. I'm happy to buy this principle, and then you have a reason not to believe in the existence of PR box. Of course, this is telling you why this point is not possible, but then you would like to reach this point, the quantum region. Okay? And then, I mean, Popescu, Burman, and Linden, and some others were able to show that even if you have some noisy version of the PR box, you could use this noisy version of the PR box to make communication complexity trivial. I mean, unfortunately, they didn't reach this point here, but at least they show that even if you had non-extremal non-signaling correlations, you could use this non-triviality of communication complexity to falsify some of these supraquantum correlations. Okay? Well, this is one of the attempts to prove this, to really bound this set of quantum correlations. Well, a second attempt was by Marcin Pawlowski and people in Singapore, in Bristol, Gdansk. I think I'm not forgetting any of the groups involved in this. And it's information causality. I'm not going to explain what is information causality. I mean, sometimes it's written like this, but this is almost a tautology. Okay, so I wouldn't put my. I mean, this is some sort of. They define a protocol where the amount of sort of information you can exchange in the protocol has to be the communication you send in the protocol. Okay, I mean, I can explain it to you if you are interested, but I think it's beyond the scope of the talk. But they have a principle that looks reasonable. And the nice thing to me is that I think it's one of the few cases, or it's the first case where someone was able to reach this quantum point. Okay, so they could show that if you were able to violate the CHSH inequality by more than the quantum violation, then you would be violating this principle. Again, in all these there is some sort of personal taste. Okay? They give you a principle, you may like it or not, and then you prove things according to this principle. So what they proved, they gave a principle that was reasonable, and they proved that you could reach the quantum violation of the CHSH inequality using this principle. It is open whether it gives quantum correlations. And one of the problems of this principle is that operationally it's very difficult to deal with. So I can give you some correlations and tell you, are these correlations compatible with information causality? It's very difficult to answer this question. This is why I would say it's open whether this principle can give you quantum correlations. Then there is also another principle that was proposed by Navas-Quest and Gunderlich. And basically what they tell you is that we are happy to believe that you have non-locality in the quantum world, but we don't see any Bell violation inequality violation in our work. Okay? Somehow they formalize this idea that you have non-locality at the macroscopic level, and the principle they call it macroscopic locality. And again, this principle also gives this point. Okay? When I say this point, it doesn't give all this shit here. It simply says that you have this point it gives a given point in the quantum boundary. But also they prove that the set is larger than quantum correlations. So macroscopic locality is not enough to get quantum correlations. You can prove that some supraquantum correlations are incompatible with the principle, but there are some supraquantum correlations that do not violate the principle.
So if these two sets are overlapping, the set of the information causality and macroscopic causality?
Well, we don't know because we don't know the set of information causality. So I don't know how they are related. Yeah. So do I know?
There's some missing gap on the corner of this polytope that information causality doesn't cover. So I was wondering if there's the same sort of corner that the microscope.
Okay, so if you want a picture, okay, this is the no signaling. This is the quantum. Okay, so you can get down to here. This is information causality and macroscopic locality. Okay. So here, what happens here? I can tell you what happens for macroscopic locality. For information causality, I don't really remember how it compares. But still, the problem is that okay, what I can hope is that information causality may be stronger than macroscopic locality. Prove the opposite, I think, is difficult because we don't know the limits of information causality. It's very difficult. Yeah, I'm sorry. And okay, so these were principles that somehow are formulated in terms of the correlation of the probabilities that you see in experiment. And then together with Miguel Namasquez and Stefano Ironio, we gave a different approach. We derived a hierarchy of mathematical conditions that tell you when you have quantum correlations. I mean, this is a non-trivial question. I can give you some numbers here, and I can tell you whether these points are quantum. And it's very difficult to answer this question because you have to look for all possible Hilbert spaces and look whether there exist states and measurements that are achieve these numbers. And we found a different way of approaching this problem that gives quantum correlations. But I mean, this is not a principle. It's simply a construction that tells you whether some points are quantum or not. So there is no operational meaning associated to this construction. Okay, so now this is you will see I have a long introduction to motivate you, okay, to listen to me. I hope I don't fail. So this, I was telling you why we are interested in this problem, why we want to bound the set of quantum correlations. Again, it's because I don't like the fact that there is no Hilbert space and state and measurements giving me these numbers. I would like something different. Now I will tell you why we want multipartite principles. And this, I mean, the starting point of that was something that we found together with the group of Gleason and Stefano Pironi as well, that was involved in that. And also Nicolas Brunner from Bristol, which is a task that we call guess your neighbor input. So it's a very easy game. Okay, so you have the n parties, and each party gets an input. Now you can think of this as a game where there is a referee, and the referee gives inputs to the parties that cannot communicate, and the parties have to generate an output. So you see that the parties are given an input here, and they have to produce an output, and the role of each party has to guess the input given to the neighboring party. Okay, so and whenever you achieve, the parties manage to guess the input of the neighboring party correctly, then they win. Okay, so the figure of merit is this probability here. You see, first party has to guess the input of the second party, who has to guess the input of the third party, who has to guess the input of the nth party. Okay, you do it like this, and we do it like a ring. So the nth party has to guess the input of the first party. It's a kind of game with no particular meaning, but it's a game. Well, then you can see it's relatively simple to show that if the parties had access to classical, quantum, or any sort of non-signaling correlation, you can this number is bounded by 2. Okay, so it's a task for which classical, quantum, and non-signaling correlations give you the same. So it's a boring game. We don't see any distinction between these sets. The interesting thing comes when you introduce some promise on the inputs. So here in my previous example, I was saying that all possible inputs are all combinational inputs are possible. So I can, in my scenario, I'm taking that there are 3 bits that are given to the 3 parties. So I have 8 possible combinations of inputs. All of them are equally possible, and this is why I sum over all probabilities. But now I will make a promise. The referee says to the parties that the inputs can be whatever, but the sum of the inputs is 0. This is a promise. And I encapsulate this promise by using this function. Okay, this is a function of the input, and I assume that this function is equal to 1 only when x1 plus x2 plus x3 is equal to 0. Well, what you can see is that whatever the promise is, the local and quantum bound is always the same. But the nice thing is that for some promises, the non-signaling bound is larger. So, in particular for the promise of the parity, whenever x1 plus x2 plus x3 is equal to 0, then you can prove that the non-signaling correlations allow you to get 4 over 3. So, and this is the task. This is guess your neighbor input with the promise that the input, you can see that the inputs here always sum up to 0. Well, this is, I would say, it was something that surprised us. Because this guess your neighbor input has some sort of flavor of no signaling. Okay? Because what you want to do, I mean, what is no signaling? I get an input and you try to guess, if you are able to guess my input back with some probability, I'm getting information about your input. And here is some sort of no signaling, but in a distributed manner, some sort. Okay? But of course not. So this bound equal to 1 is, we saw it as some sort of no signaling, but of course, even if you violate this condition, up to 4 over 3, you cannot use it for signaling. No signaling bound is 4 over 3. So, well, it worried us a little. Okay, we were thinking about this. And then we also generalized this for more parties. And you can see that in all the cases, the local and quantum bound is equal to 1, and the non-signaling bound is larger. And it's the first task where you have a non-trivial task where you have a quantum violation. So you remember the picture I put here with the classical and quantum and so on. So there is no quantum. This was the classical bound. This was the quantum. There was the non-signaling. So for this task, there is no quantum bubble. So it's a task where really classical and quantum achieve the same, and there is no quantum violation for this particular part of the correlations. So we were puzzled with this. We don't know of any situation like this in the bipartite case. Okay, for all the examples we know, whenever you have a classical facet, you always have a quantum violation. Okay, that was one reason why we were seeing that something weird was happening in the case of multipartite systems. The second thing was related to the Gleason theorem. So the Gleason theorem is something that is defined already for a single system, and is some sort of mapping from quantum measurements to probabilities. So imagine I changed for a while my scenario, so I buy all the measurement of the measurement structure of quantum mechanics. So what is a measurement? It's just a set of positive operators that sum up to the identity. And now I want to consider those maps that map quantum measurements into probabilities. Usually in quantum mechanics we do it with a trace of a quantum state and the measurement operators, but now I want to consider any possible map that I can imagine. So given a positive operator that is in a given measurement, I want to map this into a probability. And I want to do it in such a way that if the measurement, I have a measurement, so the sum of the operators is equal to the identity, I want the probabilities to sum up to 1. Okay? So these are the maps that I want to consider. And then Gleason proved that all the maps that have satisfied these two constraints can be written as R quantum maps, the trace of a quantum state with the measurement operator. So here you are, from the very beginning, you are taking the measurement, the structure of quantum measurements. You are imposing this, and you want to map this into probability distributions, and you can see that the maps are given, are the ones given by quantum mechanics. Okay, now let's try to do something similar, but now for two parties. And the theorem was generalized to the multipartite scenario by several people, and what you demand is the following. So now you have a measurement for Alice, you have measurements for Alice and measurements for Bob. And of course you want a map from a measurement by Alice and a measurement by Bob to a probability distribution. And now I will impose no signaling. Okay, so I will impose that whenever I have, well, I will impose first normalization, as before. Okay, when I have a resolution of the identity, I want the probability sum up to 1. But I also impose some no signaling. Okay, whenever I have something like this, so you see here, I take two complete measurements for Bob. So when I sum over Bob's result, I want that what I see is the same for Alice. So I impose no signaling also on this map. And well, several people I give here to point to references prove that the map that you have can be written as a trace of an entanglement weakness with the measurement operators for Alice and Bob. An entanglement weakness is an operator which is positive on product states. It doesn't have to be positive, but it's enough if it's positive on product states. And you can easily see that whenever you have a map that is like this, you satisfy all the constraints above. Okay, because it's product and product state, so it gives something positive. If you make sums, the sum you can put it inside the trace, and then you can see that it's trivially true. Okay. So in principle, this suggests that the set of Gleason correlations is larger than the set of quantum correlations, because you have some operators that don't have to be positive on all states, but it's sufficient if they are positive on all product states. But it was proven by Barnum et al. And also by us that this is not the case. For two parties, Gleason correlations are identical to quantum correlations. But then what we prove is that Gleason correlation, when you go to more parties, violate Gleason input, and then they are larger than the set of quantum correlations because Gleason input is not violated by quantum correlations. Well, this you can skip. I mean, but in order to do that, we use some traits based on some bounded entanglement states constructed from UVDs. Anyway, what is important is that Gleason correlations do not give you the set of quantum correlations for more than two parties. And surprisingly, the proof came again by this Gleason input. Okay, and the last thing is something that we also did more recently, which is the following. So let's try to, all the principles that I told you before were formulated in a bipartite scenario, like information causality, non-trivial communication complexity. So now let's try to use these principles in a multipartite scenario. Well, we don't know how to generalize information causality to multipartite scenarios, so I will do something a straightforward generalization. So I have now a scenario of, say, 5 parties, and I will say that the correlations I have are compatible with information causality or any principle, you name it, and I will tell you this generalization, whenever all the splittings of the parties into 2 groups satisfy this principle. Now I can use the bipartite principle because I can split the parties into 2 groups. So in this particular case, for instance, this is a splitting of 3 versus 2. So if I see that I don't violate information causality here for all possible splittings of the parties into 2 groups, I say that this 5-party distribution is compatible with information causality. This is a possible generalization. I'm not saying that it's the right one. It's a possible generalization. And why we chose this generalization is because this is the way you generalize non-signaling principle to more parties. Okay, when a multipartite distribution is compatible with non-signaling? Simply whenever there is no way of putting the parties into different groups so that one subset of the parties can signal to the other subset of the parties. Okay, so we took the generalization. And what we could prove is that there are supraquantum correlations that do not violate any principle in this scenario. Okay, so we had some tripartite correlations for which we can prove that any bipartite object that you construct from these multipartite correlations does not violate any principle because they are basically classical, but these correlations are supraquantum. So if you take this generalization of principle to the multipartite scenario, no principle will give you quantum correlations. And again, we show that because they violate Keynesian input. So which means now that because of these reasons, we were motivated to find multipartite principles. Okay? So I think in order to better understand the set of quantum correlations, we need new concepts that really reflect this multipartite structure. And again, I think also something that we need is something that goes beyond even non-signaling principle beyond the non-signaling principle. Non-signaling principle is also something that is intrinsically bipartite. Okay? So we like also to have something that you can see as some sort of intrinsically multipartite definition of non-signaling principle. So all this is the long motivation. So we were, by several reasons, we were forced to consider this multipartite principle, and this is a possible candidate for that, which is local orthogonality. And the principle is as follows. So you see here, I will go back to the scenario I told you. I have these boxes with inputs and outputs, and what I will define, the principle simply says that the outcomes of the same measurement by one of the parties define orthogonal events. Okay, so here you have, I call it event E1, and here you have the inputs from x1 to xn and the output a1 to an. It can be any event that you can imagine. And now I take a different event, E2, and now the inputs are different in principle from the previous event, but for party I, where party I is measuring xi in the 2 events. And I take it, so x1 and x1 prime are different. But only xi is equal to xy for the 2 events. And I take a different output for party I. So I would say that these 2 events are incompatible or orthogonal. And this is my principle. And operationally, what I will demand is that the sum of probabilities of pairwise orthogonal events is bounded by 1. So if you take 2 orthogonal events or more, but they are all orthogonal, the sum is bounded by 1. Okay. Again, I think for these principles, everything is a matter of whether you like it or not. I don't know. Yeah, okay. I found it natural, but perhaps you don't find it. And as it's written there, you can see that this principle is always satisfied by classical and quantum mechanics. And this is very easy this can be easily understood, okay? So let me try to violate the local orthogonality condition constructed from these 2 events. Okay? So quantum mechanically, I will associate some measurement operators to the events. Okay, we'll have this is the measurement operator to event 1, and for event 2, I will have something different. But the position I will have the same measurement and different output. And what I'm saying is that the sum of the probabilities of these 2 events is bounded by 1. So quantum mechanically, I want to maximize over all quantum states and all choices of these measurements this sum. same with here. Okay, so I want to maximize this. Okay, this is the probability of the first event plus the probability of the second event. I want to maximize this over quantum states. But now you can see that this is a projector plus another projector, and these two projectors are orthogonal because at the given position they differ by the same output. So clearly, the sum here is bounded by the identity, and this is bounded by 1. Okay, this is trivial. And this simply comes from the fact that you have that the projectors are locally orthogonal. I don't know if this is the best way of saying that, but I mean, at the given position, you have the same measurement and different output, and this is enough to tell you that the two events are orthogonal. Okay, well, this is the principle. Now let's see what happens when you apply this principle to these boxes. Okay, what you can see is that for two parties, the local orthogonality correlations are equivalent to no-signaling correlations. So I could have abandoned no-signaling and tell you, okay, I live in a world where outputs of the same measurement define orthogonal events even when combined with some other measurement. And if you want to, I'm not going to prove it, but this is, again, can be easily at least understood. Let me take this particular case, and I will write a no-signaling condition. So the no-signaling condition is, say, the probability of Alice getting result 0 when she measures 0. This is probability. Okay. So here you see Alice is measuring 0, Bob is measuring 0, and a sum over Bob's result. This is clearly the probability of Alice getting 0 when she measures 0. And this is of course the same because of no signaling. Okay, even if you change the result by the measurement above, I don't make any change. Okay. So no signaling is this. I will rewrite this condition. Okay, it's the same, no signaling. Well, now I will demand here two things. I will demand this and this. Again, it's the same as I wrote before. If you divide these two conditions, the only possibility is equality. Let me prove the first one, and the same will happen for the second one. Okay. So I want to prove this. Well, okay. Now I rewrite the sum of these two terms as 1 minus the other two remaining probabilities. Okay. So this 1 minus P11 minus P10. Okay. And now I pass the 4 to the other side. Then I get a plus. Well, you can see that this is a local orthogonality inequality. Okay, because you see this here, party 1, the second party is measuring 0 and looking at different outputs, so this is orthogonal to this one, according to my criterion. Here, the first party is measuring 0 and different outputs, so these are orthogonal. You can see that all of them are pairs are orthogonal, so this is local orthogonality facet. Okay. So, well, I can forget about no signaling and say that this is my principle, and I will get no signaling. Of course, no signaling has an operational meaning that this is lacking, but it's the same. But the nice thing is that now, for more parties, local orthogonality is really more restricted than no signaling. So it's really something where you perhaps start feeling this multipartite character. And one example is get your neighbor input, because this is really a task where you can see that this is a local orthogonality facet. So for instance, take this and this, you can see that the first input is the same and the output is different. So these are orthogonal to this one. And you can take odd pairs and you can see that all of them are pairwise orthogonal, and this is why it's bounded by 1. Okay, so now we're very happy at this point. We had a principle that you can understand as no signaling when you are having two parties, when you go to more parties. It allows you to understand better why you have these weird things going on when you, these results going on when you have more than two parties. Now, okay, we have a characterization of the principle. Let's try to see how we can make it operational, what we can do to make some things with this principle. And the nice thing is that local orthogonality compared to some of the other principles is, I mean, in principle you can handle with the principle in any situation. I mean, you give me any scenario with n parties, n measurements are possible results, and a powerful enough computer, and I can give you the local orthogonality inequalities. I need a powerful computer, but in principle there is no limitation for that. And how do we get that? So what we do the following. So we construct a graph given by the events that you can have. So in my previous case you have, well, I mean, here for instance you have many events. You had, well, I mean, the events were given by the components in the vector I wrote. Okay, so what's the probability of getting 0, 0 when I measure 0, 0, the probability of getting 0, 1 when I measure 0, 0, blah 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 blah. You have all these different events, and you can see that you have n parties, n possible measurements of r possible results. You have this number of events. So you make a graph and you put at the nodes all possible different events. And whenever you have orthogonal events, you put an edge connecting these events. Just to say that these two events are pairwise orthogonal, or local orthogonal. So you see here, this is the example I gave before. So here I have an event and they have the same input, different outputs, so I connect them with an edge. This is very similar to what Alain Cabello, Simone Severin, and Andreas Winter did in a paper on contextuality. So again, you define me the scenario. You tell me the number of parts, the number of measurements, the number of outputs, and I can construct this graph, and I will put a link whenever I have some orthogonality condition. So what is now local orthogonality is a clique. Okay? A clique in a graph is a subgraph where all the parties are connected. So if you have a subgraph where you have an edge connecting all nodes, these are pairwise orthogonal events, all of them, because it's a completely connected subgraph. And these are local orthogonality inequality. And of course, the interesting inequality are those that are given by fully connected subgraph. And what you have to do then is you have to find cliques and maximum cliques in a graph. And for that, there are packages that can solve this problem. I mean, finding, for instance, the maximum clique of an arbitrary graph is an NP hard problem, but as someone mentioned me when giving this talk, I mean, these graphs in principle are not arbitrary, so maybe you can make something that is really tailored for this problem. But you can define a scenario. We downloaded a package from internet finding cliques, and then we got local orthogonality inequality. And of course, one of the inequalities we got was Gaussian neighbor input. It was there. Okay, so now we have a way of dealing with this. So let's try to apply this principle. Okay, so what we did, we wanted to test this in the case of 3 parties, and it happens that in the case of 3 observers making 2 measurements of 2 outcomes, all the extremal points, all the non-signaling boxes were listed in this paper by Stefano Pironio and co-workers. So they simply made an effort to collect all these extremal points in the non-signaling polytope, and they put all of them, they classified them. And actually they belong to 46 different classes. One of them is local, and the other one are some non-local properties. And then in a subsequent paper by Yao and co-workers, they proved that using information causality, you can rule out 45 of these points, but there is one which remains. Okay? Well, bad luck. Well, actually, this point is not as innocent, because it's one of applying our techniques. You can prove that this point, you will never falsify this point using bipartite principle. So you can apply the techniques I told you before. You can prove that whatever you do with bipartite concepts, you will never falsify this point. It's not surprising that they were unable to do it using information causality, because it was impossible to do it. And this is the box number 4. Okay, so box number 4 was surviving. Well, what we did, we took all these boxes, we took the graph, we computed cliques, and we were checking that for each case we could violate the local orthogonality. So all the points, including box number 4 that you cannot falsify using any bipartite principle, can be falsified using local orthogonality.
So in this box 4, the Scarani showed that you can't use PR boxes, the infinite number of PR boxes to simulate. Is it the same one?
I don't know, possibly. But yeah. It could be, yeah. I mean, I think there is some multipartite thing going on. And since there is multipartite, and our principle is multipartite, this is why I think you can prove that it's not quantum. Okay, so I think that was a test for our principle. You can see that all the extremal points in the 3 parties were falsified. But now I go back to the bipartite scenario, because I mean, you can think, well, I mean, why do you care about the bipartite scenario? I already said that it's equivalent to no signaling, so you cannot expect any improvement. Well, this is not true, because what happens is that the principle is an equivalent to signaling when you go to more parties. So what you can do, you can now use the idea of putting things into a network. So what we did was the following. We took the PR box, and we constructed a scenario consisting of 4 parties, and we give a PR box between the first 2 and another PR box between 3 and 4. And now we can check if this violates a local orthogonality condition for 4 parties. Well, in principle, it's not clear if you do it or not, because it's not signaling, but we know that no signaling is strictly larger than local orthogonality for 4 parties. But of course, if you violate local orthogonality in this scenario, clearly the PR box is incompatible with local orthogonality. Well, and actually it does. Okay, so we found an inequality that is violated by the PR box. So even if the principle is equivalent to no signaling, the bipartite scenario, it allows you to falsify supraquantum correlations for the bipartite case. And then we were computing the amount of noise that you can tolerate. You remember what I did here. And well, we get a point here, and then we were improving slightly, and we get 0.672, and the quantum violation is at 0.707. We're almost there. But okay, you get even in the bipartite scenario, you get significantly close to the quantum point. Okay. And I mean here, using our principle, we can beat information causality for the regions where it is known. For some regions where you know how to apply it. Okay, so we were very happy with this. I think that was beyond our expectations. So conjectures now. Okay, you can say, well, maybe the local orthogonality is the principle that we are looking for. Why not? Okay, the nice thing about these conjectures, you can state these conjectures usually are very difficult to prove you are wrong. Okay, because how can you prove that? There are so many ways that you can. Using this network, you can think of many possible network geometries so that you can falsify a given point. Okay, but we thought, oh, maybe we really got the principle. That was not our initial goal, but since it works so well. But then, there's also this principle, which is there's always someone smarter than you, and in particular case, that one was Miguel Navasquez. He said, no, I can prove to you that this is larger than the set of quantum correlations. Okay, so he found supraquantum correlations that are compatible with local orthogonality. And he was using the hierarchy of conditions that I developed together with him and Stefan. But, okay, so we know this conjecture is not true. So let's consider two other conjectures I think are worth studying. So the first one is that, okay, I know that per se the principle does not define the set of quantum correlation. Maybe it does define the set of quantum correlation when you do it at a Gleason. So instead of imposing that the map from operators to probabilities is such that you don't violate no signaling, you say that you don't violate no signaling, hoping that you get quantum correlations. Okay, this is not this. You are putting more assumptions. You see, this is not. I think here I can make this conjecture, and nobody will prove I'm wrong today. Okay, so this is the conjecture. And of course, the third conjecture I think that's interesting is that perhaps you remember that I said that Gleason neighbor input was a case where you had a quantum inequality the Bell inequality that was not violated by quantum correlation. So you didn't have any quantum bubble. Okay, you had like a facet. So here's another conjecture. All the cases where you have an inequality that is not violated by quantum mechanics correspond to local orthogonality equality. Okay. Why I say that? Well, all the known examples that we have of these are local orthogonality inequalities. And in the bipartite case, we don't have any of these inequalities. And not surprisingly, in the bipartite case, local orthogonality corresponds to no signaling. Okay, so with this I come to the conclusions. So I just wanted to tell you, the first thing is I want to tell you that I think multipartite principles are really needed for our understanding of correlation in general and quantum correlation in particular. And I think orthogonality is the first principle in this direction. Something that I especially like is that it gives you no signal in the case of two parties. Okay, so you can see it as some sort of multipartite generalization of no signaling. And also something that I like when compared to other criteria is that you can operationally apply this to any situation. Okay? You can really, if you have a powerful enough computer, list all the inequalities and see if something violates. Of course, when you combine with the network, this becomes more complicated because you have to consider all possible network geometries. Okay? But in principle, you can apply this technique. Even if the principle is equivalent to no signaling in the bipartite case, it allows you to rule out supraquantum bipartite correlation, but it per se does not give you a set of quantum correlations. And also the second message which I think is nice is that it allows you to prove the non-quantumness of correlations for which no bipartite principle can work. And with this I come to the conclusion. I finish my talk. Yes, thank you very much.
Gleason set different than the set from, or do you know any relation between them?
The Gleason and local orthogonality?
Yes.
Well, I know it's larger because the Gleason violates Gaussian neighbor input and local orthogonality does not. So for sure it's, so I know it's strictly larger because local orthogonality contains the non-signaling principle, so it cannot be larger than the set of Gleason correlations. And Gleason correlation violate Gaussian neighbor input, so I know that it's strictly larger.
Could I ask this? You can think about Gleason's theorem as coming from the requirement that probabilities are linear in POVM elements.
Yeah.
Your principles kind of uses this, at least in quantum mechanical case. There is a kind of,
No, well.
There is a linearity,
okay.
There is also the convex mixtures, like the other part.
Okay, when starting all this, my hope was that, my conjecture was the local orthogonality was quantum correlations in the case of Gleason. Okay. If you ask me, I would say that it will give a quantum correlation, but I don't have any proof of that. Of course, this would be a great result. But then, since we were getting so many results, we got excited and thinking that even it was without the Gleason assumptions. But I think it's a nice conjecture to consider. Yes.
Any more questions? Sorry, I have a question. Maybe this is putting you on the spot. Could you give a little outline of how you, of the network that violates LO built out of two PR boxes? I'm very fascinated.
Okay.
Is there a sort of a fairly simple way to see why this violates the LO condition and the single PR box doesn't?
Well, I can tell you how we got it, okay? Which is, I mean, to give you an intuition, I don't know. Well, in my case, I know that networks can be very fruitful for this sort of things. My hope was that we could find it, okay? But the way, that was actually, Tobias Fries, one of my postdocs, found this. So what he did was a very smart idea. So he did the following. And this is also what we do for the extremal points. So the PR box, you have many zeros for the probabilities. So many events have zero probability. So what he did, he constructed a graph of those events that have non-zero probability. Then it's a much smaller graph. And then you can still put the orthogonality conditions and ask for the click. And this is something that I think he even solved it analytically without any package, because he put the links and this graph was not that big, and then he really found this. And what you need, all the non-zero terms have probability equal to 1/4. So for you, it's enough you find a subgraph of size larger than 4. Okay, that can be violated. And then he saw this combination of 5 probabilities that gives this. You have the violation. Of course, then to get the 0.72, we have to take all the software and things like this. I don't think it's an intuition, it's simply the way we proceed.
Any more questions? If not, let's thank all the speakers for this session.